In this video, we're going to explore the allylic system. And what do I mean by that is simply looking at scenarios in which we can produce either allylic cations, allylic radicals, or allylic anions. And if we take a look at kind of the orbital picture of allylic systems, we see that these three systems are actually fairly close to one another, right? The allylic cation has, we know that carbocation is sp2 hybridized, and so it has a p orbital in it, and so we can draw the three p orbitals of, the double bond has p orbitals, the carbocation has p orbitals, and we know that there are 2 electrons in the system. Now the allylic radical, the only difference between the allylic radical and the allylic cation is that you have an extra electron, and so we call this a 3-atom, 3-electron system. So carbocation is 3-atom, 2-electron, and the radicals is 3-atom, 3-electron system. The anion is a little bit more complicated, but we could project that we now have a 3-atom, 4-electron system. It becomes a little bit more complicated than that because typically carbanions we consider as sp3 hybridized. But if we think about that allylic anion as sp2 hybridized, then again we see that we can get delocalization of 4 electrons through 3 carbons instead of having 2 electrons on 1 carbon, that concentrated charge. So let's look at the cation first, and we can explore its chemistry through either SN1 or SN2 substitution reactions. So we're going to look at both of those, and the first one we're going to take a look at is an SN1 reaction. So recall that when I take tert-butyl chloride and it undergoes solvolysis, right? So in this case, it's undergoing hydrolysis with water. This is a substitution reaction. We say it's SN1. We're forming a carbocation, right? In this case, we would form a tertiary carbocation, and the product of this is tert-butyl alcohol. So we go from tert-butyl chloride to tert-butyl alcohol. And we studied this a lot the first semester and saw that the rate of SN1 substitution of this reaction was greater than for secondary or primary alkyl halides. Now, when we compare this reaction to that of an allylic system, so in this case, all I've done is added a double bond to one of those carbons. And I, of course, I'm going to develop an allyl carbocation, and so I'm going to get 2 products based on that allyl carbocation. And I see this reaction is 200 times faster than the simple hydrolysis of tert-butyl chloride. And the reason for that is very simple, because the allyl carbocation that's formed isn't simply a tertiary allyl carbocation, but it is resonantly stabilized and produces a package of this allylic carbocation. So we can see that through that resonance stabilization, it leads to a lower transition state, which means that the reaction is going to go faster. When we look at substitution reactions of allylic halides that undergo SN2 mechanism, we also see that they are faster than alkyl halides that undergo SN2 substitution. And so we can take a look at a simple case where we have a primary alkyl halide, right? So here I have 1-chloropropane, and I'm reacting it with sodium ethoxide in ethanol. So SN2 substitution, the ethoxide is going to attack the carbon and chloride's going to come off, remember, at the same time, and I produce an ether, right? And I know that based on SN2 mechanism, this is a relatively fast reaction. Now, if we simply add a double bond there under the same conditions, right, reacting with the same nucleophile, I get the same ether product, and I see that this reaction relative to the reaction above is 37 times faster. So one of the things that, it's easy to justify why allylic carbocations would stabilize an SN1 mechanism, but how is it that that allylic system is actually stabilizing an SN2? Because there, we say that there's no carbocation that's building up, so how, and of course you see that we don't get rearrangement or anything like that. So how is this possible? Well, we can think of it at a molecular orbital level, and we see that the pi bond actually helps to stabilize the transition state. And if you recall, the transition state of an SN2 is this pentacoordinate carbon, right, where the nucleophile is coming in and the chloride comes off at the same time. We say it's in concert with one another, right, a concerted mechanism. Now, if we take that picture and instead of having an ethyl group coming off of the carbon, we have this ethylene group coming off of the carbon. And we see that the ethylene has these p orbitals, right? And those p orbitals can overlap with the pentacoordinate transition orbital, right? Because remember, this orbital is kind of strange. It takes the carbon's sp3 hybridized, but at the transition state, that sp3 hybridization almost goes into an sp2 hybridized system where you have a p orbital on that carbon, where the nucleophile is coming in and the halide is coming off. And so you can see at that transition state, you can have a stabilization by donating electron density through that pi bond to help stabilize it. And if it stabilizes the transition state, lowers the activation energy, increases the rate of the reaction. All right. Briefly, we're going to look at or talk about allylic radicals, because we've already seen in chapter 12 essentially the effect that resonance stabilization can have on allylic systems. And an example of this is when we take cyclohexene and react it with NBS in the presence of light. So remember, NBS produces a small amount of bromine, right? And so that bromine then dissociates with in the presence of light to give you bromine radicals, and that bromine radical then abstracts a hydrogen. And we see that the allylic hydrogen is the only one that is abstracted, which leads to the formation of the allylic bromide. And so this is via radical formation, which can be stabilized through resonance. So now let's look at the allylic anion, and this one's a little bit harder to kind of see, but when we're talking about anions, we're talking about a system that loses a proton, and so we can think about the acidity of these systems, and we can compare it to the acidity of an alkane. So we know that alkanes are not very acidic, but if they were to lose a proton, the conjugate base would look something like this, right? We would form a carbanion, just a normal carbanion, of course, through the loss of a proton. And we know this isn't very viable, and the pKa is very high, 50 to 60. It's actually really hard to measure because we don't have very many bases that can actually abstract a hydrogen that is so weakly acidic. Now, if we compare this system to an allylic system like 1-propene, excuse me, and again I'm highlighting the hydrogen that I'm going to be removing it's an allylic hydrogen now, and I see that if I remove an allylic hydrogen, I get this carbanion. Now, treating that carbanion like an sp2 hybridized carbon, I see that I can draw a resonance structure. And so that resonance structure is going to delocalize that negative charge, which means that we can predict that the because the conjugate base is stabilized, then the acidity should be enhanced. And indeed, the pK is 43, so it's a little bit lower, which means that it is more acidic than your typical alkane is. And so we see that it's easier to remove a hydrogen due to the stability of the conjugate base.